Okay, hello all you crazy people out there. My name is Michael. I like wizards and dragons and making games. Today we're going to finish shadow mapping, at least for directional lights. So in the last video, I did a bit of setup for shadow mapping for directional lights in the form of rendering the scene from the point of view of a light to a secondary surface, specifically its depth information. And today, we are going to use that depth information to cast shadows on a 3D scene. Since I recorded that first video, there have been a lot of people asking about how to do shadows in 3D games, and I hope this is timely. I hope I'm able to get this video out soon enough to be of use to everyone who's been asking that. So if you haven't watched the first video, go do that. One little detail that I feel a little bit obligated to mention. There is a particular post on the GameMaker forums about directional lights and casting shadows in GameMaker. And it's been around for a while, and a lot of people have followed it over the years. And I really feel bad about throwing shade at other GameMaker tutorial makers on the internet. A lot of people have tried to follow this tutorial, and a lot of people have also gotten a lot of use out of it. But I unfortunately don't think it's very good. I think it doesn't explain a couple particular things very well, and I think that it's caused a lot of confusion among some people who have tried to do shadow mapping in GameMaker in the past. And because of that, I think it's also caused a lot of people to give up trying to implement shadows in 3D games in GameMaker. If you happen to be one of those people, I hope you find that this video is a little bit more straightforward and easier to follow. And I hope you find that while casting shadows is definitely complicated, it's not as complicated as maybe you might have thought. If you happen to be someone who did follow that forum post in the past, and if you did get use out of it, then I'm glad you were able to get use out of it. I know that a lot of people have. I know that the post has been around for a while. I don't know if the post author has any plans on updating it in the future to clarify things that might have caused people to get tripped up on it. But before getting started, I just feel that is something I should mention because I know a lot of people have encountered that in the past, and well, the outcomes have been mixed. Let's just put it that way. With that out of the way, let's move on to greener pastures. Let's talk about shadow mapping. So this problem is more or less shaped like a number of other problems that you might have tried to solve in GameMaker and shaders in the past. Figuring out the distance of a fragment to a camera is fairly straightforward. You probably have done it before. In fact, if you're following this video, I know you have done it before because that is how we are rendering the depth value of each fragment in the first place. If you've ever tried to do something like pixel fog, you have probably tried to do something very similar. Just instead of using a normalized depth value, you've probably used an absolute depth value. Unfortunately, in this particular case, it's going to be a little bit harder. Instead of doing something like GM underscore matrices, matrix world view, let's say, times object space position, and then maybe you would get the length of this vector. This would give us the distance from each vertex to the camera that is actually rendering. In other words, the distance between each vertex and our eye, rather than the distance between each vertex and the light source, which is what we're looking for. And that might seem like a bit of a problem at first, until you remember that what GM matrices, matrix worldview, and so on and so forth actually are. This is simply a uniform constant that is automatically built into each and every one of the shaders that you write in GML. There's nothing special about this value. This is just a uniform constant as a 4x4 matrix. And if you wanted to, you could pass your own uniform map to a shader. And passing matrices to shaders as uniforms is not something that I've explicitly talked about in the past, but it does work pretty much the same way as any other uniform value. We can say uniform map for, I'm going to give this a name, let's call it, lately I've been prefixing most, if not all of my uniform constants with U underscore, just so that I can tell them apart at a glance from other things. So let's call this U underscore light view mat, and let's define another one for now, uniform map for U underscore light proj mat. So this is the view matrix of the light, and this is the projection matrix of the light. And what the view matrix of the light is simply going to be up here, where we render the depth texture. The view matrix for the light is going to be this matrix build. Look at x from y from z from, so on and so forth, where x from y from z from is the position of the sun. And the projection matrix of the light is going to be matrix build projection ortho, the size of the shadow map, the clipping planes for the shadow map. and those are passed into the currently active camera. The settings are applied, you draw all the stuff through that camera, and then you reset the surface to come back to the normal 3D world. If we wanted to use these matrices in another shader, I'm going to, instead of using the same viewmat and projmat variables that I was using before, let me give these somewhat more helpful names. Let me call this light viewmat, light projmat, and we are going to assign the appropriate matrices to these two variables, so they will not just be overwritten by the other ones later on. So when you want to actually set the uniform, when you want to actually set the matrix to a uniform in a shader, that is going to look an awful lot like setting any other uniform to a shader in GameMaker. You can say shader set uniform, and if you control space, you can see a couple suggested functions that you might want to use. There's shader set uniform f, which is what I almost always use. Shader set uniform f array, which is for an array of values, rather than a series of individual values. There's integer version, so if you wanted to, for whatever reason, set a couple of integers to a uniform in a shader, you can do that. Shader set uniform matrix, which sounds like it should be what we want, but I think that's actually, instead of allowing you to set any old matrix to a uniform, it sets the current transform matrix, which, honestly, I don't know why you would do that when you could also just, like, camera apply or whatever. And shader set uniform matrix array, which is the array version. I'm going to go with shader set uniform f array. This is for an array of floats. A matrix, after all, is nothing but 16 floating point values in a row. Or that's a matrix 4x4 anyway. Matrices of other size will be other sizes. We can get the name of the shader uniform constant with the good old shader get uniform. The shader that we're going to be fetching from is going to be the one that is currently active, shader basic 3D stuff. The name is going to be whatever I called it. U underscore light viewmat. And the array, again, matrices are just arrays in GameMaker, and also in a lot of other 3D systems. So we can just directly set the array of 16 values into this function, and call it a day. So that's the viewmat. I also am interested in the projection matrix, so we can call the same function with light viewmat and light projmat. And if I were to run the game now, it would not look any different. It will actually not run because I forgot to get rid of this nonsense down there. We are not actually using these uniforms, but it will indeed run. That is what you would want to do if you want to set a matrix to a shader as a uniform. So where do we go after this? So normally in a shader, you would do something like GM matrices, matrix worldview projection multiplied by the object space position. And that will multiply the object space position, so the position of a vertex in local space, into these three matrices, and that will transform the vertex position from local space to relative to the screen coordinates. If you really, really want to, you can build the equivalent of this of GM matrices, matrix worldview projection yourself. Past that to the shader as a uniform. I am going to close this create event tab because I am not using it and I keep opening it by accident. You can pre-multiply the world, the view, the projection matrix together, and you can have the equivalent for this single value, except instead of the camera's worldview projection matrix, it would be the light's worldview projection matrix. And that would save you a little bit of typing in shader code, but that would also kind of be a huge pain in the neck because you'd have to do that every time you set the world matrix in the draw all the stuff function. And in any case, for the purposes of a tutorial, I think I would rather step through each of the steps one by one. I use this comic a lot to illustrate exactly what is happening when you multiply a position by a matrix in a shader. And I'm just going to leave it on like the right half of the screen for now, because I think I'm going to be talking about it a lot for the next 5 minutes. I seriously owe this artist lunch or something. So first, as with any other shader, we're going to want to transform the vertex position into world space. Then we're going to want to transform it into camera space, or as some like to call it, into eye space. But instead of eye space relative to the camera that we're rendering through, we want it to be eye space of the light. After that, we will transform into screen space. Again, relative to the light, we can multiply by the projection matrix of the light. And then we will have the equivalent GL underscore position for each vertex relative to the light. So I'm just going to start typing this out now. Let's say vec, not var, we can say vec for world space is going to be GM underscore matrices matrix world multiplied by vec for in position 1.0, or just 1 or 1 point, whatever you want. This is going to be the vertex's position in world space. We have the eagle eye observers among you may notice that this is pretty much exactly the same thing as v underscore world position, just the full vector 4 instead of the vector 3. And again, if you pre-multiply the world matrix with the light's view matrix with the light's projection matrix ahead of time in the draw event, you can do some of these computations on the CPU exactly once and not have to do these matrix multiplies for every vertex that it runs on, but there is going to be some amount of redundant code in this vertex shader in this video because my goal here is to explain what it's doing and not to minimize the number of machine instructions. Next, we should be able to do something that is more or less analogous to what we did in the depth rendering shader, where the light depth varying for each vertex is equal to glPosition.z divided by glPosition.w, and we can set up our own varying. Is it a vector? It's a float, isn't it? Varying float v light distance. And we can say v underscore light distance is going to be equal to screen space dot z divided by screen space dot w. We can carry this over to the fragment shader, let's say over there. So this is good for getting the distance between each vertex / fragment and the light source, but we also need one more bit of information if we want to be able to sample from the texture, from the depth texture. And that is going to be the corresponding texture coordinates of where each vertex would be on the depth texture. And the way that we can do that is by emulating the little bit of math that'll happen between the stages of the vertex and the fragment shader in the graphics pipeline. There is a little bit more that happens between the vertex shader and the fragment shader. GameMaker does not currently give us access to all stages of the graphics pipeline. Fortunately, it's not a lot of math, and we can just do the relevant bits ourselves here. So the screen space vector. The XY components of this screen space vector 4 will be where on the screen each vertex ends up. This vector, the XY components of this vector will have a range of, instead of from 0 to 1 like we normally like to have our texture coordinates to be, this is going to have a range of -1 to +1, so we're going to have to just adjust the range of this vector real quick, and that is converting a value that is within a range of -1 to +1. This is something that I've done in a number of videos now. We're just going to multiply by 0.5, so we're going to cut the number in half, and then we're going to add 0.5. And I believe I also need to do a perspective transform for this as well. So screen space.z. You can throw some extra parentheses around this if you want, but order of operations dictates that it would happen in the right order regardless.
Hey.
This is going to give us the value between 0 and 1. And we can use those to serve as the texture coordinates when we look up the depth for each fragment on the shadow's depth texture. Also, and this is just how the internet works. I know if I don't say this, someone is going to bring it up in the comments. Not all vertices, when they're transformed into screen space like this, are going to have a value, are going to have an XY coordinate in screen space between -1 and +1 that we can transform into a range of 0 to 1. Vertices that are not within view of the camera will be off in the distance somewhere and will not be within that range. It is only the vertices that are within view of the camera that is true for. So that's either vertices that you see on the screen, if you're rendering through the main camera, or if you're rendering through the depth texture, the vertices that are within view of the lights camera on the depth texture. So this is just going to be the coordinates of the shadow map. I can make myself another varying. Let's call this varying vec2, because this is going to be an XY. V underscore, let's call it shadow text chord. And shadow text chord can be set equal to this, and it needs a semicolon after the end. And we can carry this over to the fragment shader. And I just want to make sure that this is going to compile, that I didn't do anything stupid. Nothing's going to happen because I have not started to use these values anywhere. Good, the world is still rendering, nothing's on fire. Now we can jump over to the fragment shader. And this recording session has been going for 50 minutes, which is a bit of a marathon, mostly because I say everything like 4 times because I don't like the way that it came out the first 3 times. But I think we're finally getting to the end. This is going to be a long video. Hopefully you see why I did not want to do this all in one shot in the first video. So, firstly, let us add a texture sampler to the fragment shader. We can say uniform sampler 2D. What do people usually prefix sampler uniforms as? S underscore? I think it's usually S underscore. I'm gonna call this S underscore depth texture. And when we go to draw all the stuff, we can texture set stage. The sampler ID is going to be shader get sampler index, shader get sampler index, shader basic 3D stuff, and the name of the sampler is going to be S underscore depth texture. And the texture ID is going to be surface get texture. You can get the texture of a surface directly. We can just get the texture of the shadow map surface. And we can pass that to the shader, and we can now sample from the shadow map surface as if it's a texture. And if you just want to do a quick sanity check to make sure that everything so far has worked correctly, this is a good place to do it. Instead of saying GL frag color equals the final color, which is just like the vertex color taking the light into account or whatever, you can say, comment that out if you want, you can say GL underscore frag color equals texture 2D, and instead of looking up the texture of GM base texture with the texture coordinate varying, we can instead, sample from the depth texture, and the texture coordinate that we're sampling from can be v underscore shadow texture, shadow text coord, and we can just see if what the world actually looks like. And I can see I did something wrong here. I was going to say we can see if what the world actually looks like is more or less what is on the shadow map texture that is being rendered in the corner. And I suppose you could say it's a good thing that I did that sanity check because something is not right. I suspect I typed a plus instead of a minus somewhere in the vertex shader at some point. Wow! This took me like 5 whole minutes to track down screenspace.xy over screenspace.z. Oh wow. I've made some dumb typos in my day, but I think that one takes the cake. So you can see that what we have on the ground is more or less the same as what we have in the on the depth surface up here in the corner. Right down to like the pixels on the ground that like would represent the tree that is where I'm standing, which is there, even though it's there and casting a shadow, even though like I am not a tree. So that's everything working correctly. I can't believe like how much time I spent looking at this code trying to find the error, and it was screenspace.xy over screenspace. Never mind. How did I survive to adulthood? So from here, I should make a compilation of the dumbest typos that I've made in these game dev videos sometime. So from here, instead of setting GL frag color directly to texture 2D, the depth texture, and the shadow texture coordinates, we can we can say vec for sampled depth color equals this or something like that, and then I'm just going to copy and paste in the from depth color conversion function from that one other video when I talked about encoding depth as color.
Hey.
And we can make use of that. We can say float depth value is going to equal from depth color, and the input color that is going to go into that function is going to be sampled depth color, except it's just going to be RGB because we are not currently making use of the alpha channel for depth here. You can if you want to. That would give you another 8 bits of precision, but I don't particularly feel the need to. And when you want to wrangle alpha as something other than alpha, and when you're drawing stuff, you need to do a little bit more work to make sure that the graphics hardware doesn't try to blend it automatically, which would make the enter just wholly wrong. So we can compare the depth value that we sampled off of the texture to our own depth value from the vertex shader. So we can say if the light distance varying is greater than the depth value that we sampled off of the texture, then we can just do something, for example, final underscore color RGB multiplied by equal to 0.5, and this will darken the color by 50%, and then we can set glfrag color equal to the final color. This is not quite the end of the story, but we should start seeing results about now. We are not seeing results about now. There's a couple things that could mean. One is that I made another dumb typo somewhere. Two is that I've actually made a bit of a math error somewhere else. Okay, so as if the typo I had a minute ago wasn't dumb enough, I copied and pasted the wrong version of the from depth color function from a different project that I had that figured this out in a different way. What am I going to do with myself? So I run the game now. We're going to see something that sort of resembles a shadow. We have our tree shadow standing in front of us. If we go behind the pirate ship, we have something that definitely is sort of shadow-like. However, you may notice that something's wrong, and that is that we have a little checkerboard pattern all over the world. And this is, I believe the pros like to call this shadow acne, and you can sort of imagine why. The reason that this happens is because floating point calculations sometimes mean a certain loss of precision, and it sometimes means that when it comes to very, very small degrees of precision, sometimes little bits of inaccuracy tends to show up, and that leads to this wonderful, wonderful hypnotic checkerboard pattern that's all over the game world right now, because individual triangles, individual fragments are sometimes not being correctly evaluated as being like in front of or behind the value that's sampled from the depth texture. And dealing with that is a little bit, just a small amount of extra code. Instead of saying if v underscore light distance is greater than the depth value, you can say if v underscore light distance is greater than the depth value plus some nominally small amount, let's say 0.1. And this will make the shadow acne problem go away and cause a new one to appear. And that is that the shadows are gone. Do I want to make that much, much smaller? I probably want to make that much, much smaller, don't I? I think my test project used 0.01. And here we go. So the shadow acne is gone. We do indeed have shadows being cast from things such as the tree and from things such as the pirate ship. This also includes self shadows, so things behind, for example, the mast, the big flag of the pirate ship. That's the mast, right? I know my pirate ships. Is casting shadows on the part of the ship that's behind it, as well as on the floor and on the balls and on presumably me, although I don't exactly have a visible player model or anything like that. You can sort of see like the roots of the tree that is pretending to be me. This isn't the perfect fix. There are still a couple of places, such as this random bit of flag up there, where we're sort of fighting with ourselves, where like a shadow is being cast, or maybe it should not be. Actually, oh wait, is that? Okay, never mind. That's not fighting. That's just the flag casting a shadow on the things below it. Okay. It's still somewhat of an undesirable effect. If you want to play around with this 0.01 value, you can increase it a little bit, and that should cause some of the accidental shadowing to go away. However, it is also It is also starting to cause a new problem to become apparent, which is that the shadows of things like trees are doing a little bit of levitation, and the shadows are not appearing to be connected to the base of the tree trunk, for example. This is called Peter Panning, appropriately named because the shadows are appearing to, you know, levitate behind the thing that is casting them. Graphics programmers are the best at naming things. There are ways to mitigate that. For example, decreasing this bias value. This is called the this is generally called the shadow bias value, by the way. If you want to make that a named variable instead of just a magic number. There is a bit of a trade-off between the Peter Panning effect and the shadow acne effect. You can see that with a smaller bias value, the trees appear to be a little bit more connected to the shadows, but you may see a little bit more by way of like inaccuracies with shadow acne coming into play. I believe there are other ways that you could try to tackle both problems at once, although I did not write down any of them in my notes.
Hey.
I may leave links to other literature about shadow mapping in the video description. I think I'm going to leave it here. I think I'm going to leave the bias value here for now at 0.05. I think that is good enough of a trade-off. You know what? I am curious. This one here, opengl-tutorial.com, is I believe where I got most of this from when I did this on my own the first time. As you can see, there are a number of things you can do to make the shadow map evaluation a little bit sharper, but I think this is a little beyond the scope of this video. I might revisit this someday to do more advanced things. Anyway, getting back to the main event. Some other things. The size of the shadow texture is not infinite, and if you were to... Everything that's within the game world right now at the moment is more or less within the confines of the shadow texture, so it's not hugely evident that there might be any, like, problems with the finite size of the shadow texture. Although if you go all the way over here to the corner, you can see that this corner is just slightly falling off the sides of the shadow map, and you can see that if you try to sample anything from beyond it, the color that will be sampled outside this range, it depends on your texture wrapping settings. If it's set to clamp, it'll just be whatever the value on the edge is. If it's set to wrap, it'll wrap around and be weird. But you can see that there is a shadow that is sort of falling across the corner of the map here that should not be there. If you were to make the shadow texture smaller, the shadow map size is currently 2048. If you were to make this instead, let's say 512, significantly smaller, a quarter the size in each direction, this problem will manifest itself much earlier. And there also appears to be yeah, I think these errors down here are caused by the texture wrapping settings. It kind of looks like bits of the Going Merry are casting a shadow all the way over here, thanks to the texture wrapping, because this part of the world is sort of falling off the sides of the shadow map. What I generally like to do to deal with this, and I don't know if there's a better solution, but I like to, instead of having a fixed position of the sun's XYZ, I like to instead have it follow the player around, and that might look something like, where is, you know, I'll just put it in the beginning of the draw event, like up here. Sun XYZ can, instead of being its original values, it can be something like player.x minus 200, player.y minus 200, and then z is going to be player.z plus 200 or something akin to that. And this will cause the sun to sort of act as an overhead camera that follows the player around. And you can see that, and it's still wrong because the surface is minuscule, but you can see that the camera rendered from the point of view of the light source is now following me around, and at least now things that are sort of nearby me are casting shadows correctly. Let me increase the shadow map size at least somewhat to 1024. All right, that's a little bit more acceptable. The fall off of the shadow is now not happening until farther away, and more of the things that are in my immediate vicinity are at least casting shadows correctly. Again, I don't know if there are like better and more preferred solutions to this. Ooh, you can kind of see that the trees are self-shadowing from behind as well. Might want to use a slightly smaller depth bias value to account for that as well.
Hey.
Anyway, now I can pretty much run wherever I want in the world, and we'll be able to have at least some degree of shadows around me. There is an argument that the internet likes to have sometimes about whether or not it's a better idea to in a 3D world transform the camera's position through the world and have the world's position be static, versus having the camera stay at the world's origin and just transforming the world around the camera. And things like this is definitely a reason to do the former, because that would mean that you don't have to worry about positioning the light every frame. You don't have to worry about calculating where the light camera should be. There's also other bits of floating point madness that play into that as well. Other problems, you may notice that the shadows that are being cast, even when they're being cast correctly, are slightly jagged, and that in turn is also due to the finite resolution of the shadow texture. If you wanted to have a higher resolution shadow texture, but in a sense zoom it in a little bit, this would become more smooth. If I were to go back to having a 2048 size shadow map, but instead the projection matrix size of the light would be something like shadow map size divided by 4. This will result in a smaller area that the shadow is that the shadows are like calculated correctly on, but it will result in a much sharper outline around where the shadows should be. So that is another potential trade-off that you can have. As nice as it would be to just like crank shadow map size all the heck the way up to like, I don't know, 16 384 or something like that, and you could have a huge shadow map size with a decent resolution. That is a tremendous amount of video memory that would consume. A 16K by 16K surface is I believe a quarter of a gigabyte of video memory. It's a lot of pixels to fill, and you can see that the game is slowing down. So I would recommend not doing that, even though it does produce sharp shadows and you can see them way off in the distance. Let's see, that's another trade-off. I think I'm gonna stick with 2048 by now, and I will have the shadow map size divided by 2 in the ortho camera dimensions. Let's see, anything else? It's still a little bit jaggy, but it's definitely better than what it was before. All right, any other notes? I think that's about it. Like I said, I might someday make a couple other videos on shadow casting with directional lights in ways that, like, specifically about things that would help you clear up some of the issues that emerge when you do this. There's also, of course, the matter of casting point lights and spotlights, casting shadows from point lights and spotlights. Those would have you do a little bit of what is called cube mapping, which is going to be a little bit of additional work to set up. Directional lights are undoubtedly much simpler to set up when it comes to shadows, but I do want to do at least point lights when it comes to shadows eventually. Other ways of doing this, light mapping. I did mention light mapping at the beginning of the last video. That is something else that is worth talking about. Light mapping is when you essentially pre-compute where the shadows fall on the world. Light mapping involves baking the shadows into the world ahead of time. It typically consumes a lot of texture memory because you do have to have a separate like bit of light map texture for every surface in the game world. But it is very fast because you don't have to bother rendering the texture beforehand. It's sort of like doing the depth texture encoding beforehand when you build the game, so that you don't have to compute it at runtime. But at the same time, that does come with its own costs. Again, typically uses a lot of video memory. It does involve a little bit of work up front before you build the game, and it does not allow for dynamic shadows because the shadows aren't being computed in real time every frame. And then there's the matter of ray casting, which if you want ray casting, go talk to this mad lad. So, that is it for me for now. If you want the code for this, look for the GitHub repository down in the video description. I had not been committing changes incrementally because I have not been remembering to do that. So I should probably split this into pieces and do that before I push it live. Otherwise, I try to post about 2 game dev videos a week. I've been taking a bit of a break in January/February, but I think soon I'm going to try to get back into the twice a week routine, barring potentially unforeseen demands on my time that might arise. Otherwise, I have a Patreon, so if you want to contribute towards these videos being made, there'll be links to that in all the usual places as well. You could see some fun things like your name in the credits. You could hear a verbal shout-out of your name at the end. I post a preview of my future plans about once a month. And if you wanted to pledge, I would definitely appreciate it. I hope you all found this useful, and I will see you all later. Special thanks to Army Armbuster, Edward Holt, Emily Koyo, GameMaker, Gunnar Clovis, Posho, Sindra Larson, Squarecrow, The Nothing Happened, Tusk, and Zenjamin for supporting these videos. If you want to see your name in the credits or hear yourself shouted out at the end, head on over to the Patreon page down in the video description to join the fun.